So today we're going to continue our discussion about strain gauges, and today we're going to focus specifically on how do we work with or develop stress-strain relationships for rosette strain gauges. So there are a couple of different types of rosette strain gauges that you can utilize. Some of them can be seen schematically on this next image here. So we are going to focus on specifically these couple of types. So rectangular and equiangular delta. So if we look at our presentation, let's kind of scroll down here for a little bit. You're all experts in this. We can use several different types of strain gauge rosettes. So rectangular delta, we're going to talk a lot about. You can also use T delta. So you'll notice each of these, this has basically 3 arms. This has 3 arms. And here, this T delta has basically this 4 arms. So you use the T delta basically to kind of confirm. You basically kind of calibrate, or you can kind of double check your answer by setting D, your 4th arm, at some kind of arbitrary rotation, either where you know what the strain is in that direction, or you can kind of align it with a different strain gauge to kind of confirm that your strain gauge rosette is working. But we're going to focus primarily on these two in a bit. So there's lots of kind of these expressions in the notes. You want to be kind of careful, and actually this expression is wrong if you look back through the textbook. But again, just like these are for calculating principal stresses, principal strains, kind of rotations. Just like in our Mohr circle method, I would avoid kind of using these expressions. We could approach it a lot more kind of simply by using that Mohr circle technique. So we're going to kind of talk about that right now. So one thing to notice about the rectangular strain gauge rosette. So basically the setup is like this. You have basically strain gauge, we call them A, B, and C. So I have a strain gauge oriented like this, strain gauge oriented like this, and a strain gauge oriented like this. So if I have some type of thin-walled pressure vessel and there's a crack somewhere near here, I just kind of slap on my, and I know that near this crack, obviously we can't use our, typical linear elastic mechanics. I slap on my strain gauge rosette. This is blown up, obviously. Usually it'll just go like something like this, kind of right near this area. And we can measure essentially the strain basically in A, B, and C, and then we can kind of rotate and do kind of other kind of really cool techniques here. So the angle between A and B is going to be, in this system, 45 degrees in real space. So that is our theta. The angle between A and C, we see, is going to be, this angle is 90. For our equiangular delta rosette, we have, basically I'm going to try to draw this as best as I can. So we could have A here, and here, and here. So B, C, same idea, except now the only difference is my angle is 60. So this angle here, theta is equal to 60 in real space. So this is 120, this full one between A and C. That's it. So how do we actually use the results from this strain gauge? So let's look at a typical example, and we're going to draw essentially our basically our strain, basically our Mohr circle in strain space. So let's go ahead and look at that right now by looking at an example. So I have a rectangular rosette, and I measure these two, and this should be not inches, it should be in micro. Oh, actually, no, that's fine. I measure these 3 kind of strains in my A, B, and C arm. So again, I have my rosette, A, B, C. This is 45 degrees. And I measure that basically my strain in A is 72 times 10 to the minus 6. My strain in B is 120 times 10 to the minus 6. And my strain in C is 248 times 10 to the minus 6. Oops, excuse me. Here, let me erase that. Be a little bit nicer. That's it. So from this, we want to draw basically our Mohr circle in strain space. So we are going to put our normal strains on this axis. So oops, let me erase that. So these are our normal strains. We'll put so gamma over 2 here. So we are going to, that's your shear strains. So we have these 3 values. So we have a value at, we have epsilon sub c here. So that's at 248. Oops, excuse me. Let me erase that. epsilon sub c, this is at a value of 248. And then we have our b, which is at 120. So again, these are just, we're drawing here, these are just going to intersect, these are basically our normal strains that intersect this x-axis. And then we have our epsilon sub a. This is our epsilon sub a, and that value is going to be 72, all in microstrain. So our circle somewhere is going to intersect these points like this. So again, we need to figure out what are our principal stresses, our principal strains, and we need to figure out what's kind of going on here. So what do we need to figure out in this expression? Well, we need to figure out C, what is the center of our circle, what is the radius of our circle, and what is our rotation to theta in order to get to our principal strain state. We need to solve for the center of our circle, the radius, and 2 theta. So let's start, and we know that at some point here, we are going to kind of connect from the center, whatever the center of our circle is, some radius, and this is going to intersect, or it's going to kind of touch our kind of value, epsilon a, and there's going to be some rotation 2 theta angle that's related between all these values here. So that's one of our expressions, right? So I know if I want to figure out what is the point at epsilon a in terms of my kind of circle radius and geometry, I know that my strain at A is equal to my center. So it's going to be the center plus this point right here, right? So this value where epsilon eta falls on this graph is just going to be center times radius times cosine of 2 theta, right? It's just the projection along that x-axis. Center plus r cosine of 2 theta. Now, what about B? Well, it's going to be very, very similar expression. Equals C plus R cosine of 2 theta. But again, we can relate in this rectangular kind of strain gauge rosette. We know that A and B are related by a rotation of 45 degrees. So I could just say that 45 degrees in real space. So it's going to be related C plus R cosine theta plus 90 degrees. Oops. So let me erase that. So right here, plus 90 degrees, because of that rotation. It's the same idea. It's fixed. Like we know what that value is. We can solve essentially for that value. And once we figure out theta, and C is the same thing. If we want to relate it to A plus R cosine of 2 theta plus the 90 degree rotation, it's 180 degrees here. So that's it. So I know this value, I know this value, I know this value. We have 3 equations, we have 3 unknowns, and now we can solve. So you do the exact same thing for the equiangular rosette, except this would be, instead of 90, the angle is in real space is 60. So in 2 theta space, it would be 120. Here, 120 times 2, it would be 240. That's it. That's how you solve all of these different problems. You can kind of relate it to these different rotations. Now you have to be careful, and we're going to kind of do a lot more problems where we kind of offset some angles and do some kind of very strange and kind of unique rotations. But this is essentially the idea and the same concept. We're always relating the strain in these different arms by this other kind of rotation here, and you can always rotate around in your stress in your strain space. So yeah, that's it. We're going to do some more practice problems, but that kind of ends the theoretical aspect of this lecture. So be on the lookout. We're going to do some example problems. That's always kind of the best way to kind of learn some of these concepts. But that's about it. All right. See you next time. Bye.